Hello and welcome back to the channel. Today we're overclocking the AMD Ryzen Threadripper Pro 9975WX processor all the way up to 5625 MHz using the Asus Pro WS WRX90E Sage SE motherboard and water cooling. I do that using the traditional Precision Boost Overdrive overclocking tools. For example, Fmax, Boost Override, Scalar, and Curve Optimizer.
In this video, I break down the Ryzen Threadripper Pro 9975WX tuning process into 4 unique overclocking strategies for beginner and advanced overclockers.
However, before we jump into the overclocking, let's have a look at the hardware and the benchmarks that we're using in this guide, as well as the stock performance.
The AMD Ryzen Threadripper Pro 9975WX is part of AMD's Zen 5-based Ryzen Threadripper 9000 workstation processor product line, codenamed Shimada Peak. It's the very first Threadripper Pro I'm overclocking on this channel. Pro means the CPU has more PCIe lanes and 8-channel memory. The 9975WX still has 32 cores and a base clock of 4 GHz. The listed boost frequency is 5.4 GHz and the TDP is 350 watts. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability.
Before we start overclocking, of course, we have to check the performance at default settings.
The default Precision Boost 2 parameters for the Ryzen Threadripper Pro 9975WX are as follows. Here's the benchmark performance at stock. Here are the 3D Mark CPU profile and OCCT benchmark scores at stock. Here are the AIDA64 memory benchmark scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 4475 MHz and CCD123 effective clock is 4080 MHz with 0.997 volts. The average CPU temperature is 68.7 degrees Celsius and the average CPU package power is 349 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 4814 MHz and CCD123 effective clock is 4363 MHz with 1.063 volts. The average CPU temperature is 68.7 degrees Celsius. The average CPU package power is 349.5 watts.
Of course, we can override the power consumption limits by using Precision Boost Overdrive, and that's exactly what we'll do in our first overclocking strategy. However, first make sure to locate the Clear CMOS button.
Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch.
In our first overclocking strategy, we simply make use of enabling AMD EXPO and enabling Precision Boost Overdrive. With the launch of Zen 5, AMD introduced an improved version of their Precision Boost Overdrive 2 overclockers toolkit. This toolkit allows us to fine-tune the parameters governing the Precision Boost algorithm.
The Precision Boost Overdrive 2 toolkit for Zen 5 Ryzen processors includes the overclocking knobs from Zen Plus, PPT, TDC, and EDC, Zen 2, Boost Override and Scalar, Zen 3, Curve Optimizer, and the newly introduced Curve Shaper for Zen 5. There are essentially 3 levels of Precision Boost Overdrive. In this overclocking strategy, we're just enabling Precision Boost Overdrive, whereas in the following strategies, we'll explore tuning the parameters. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and to a lesser extent the TDC and EDC limit will help unleash the frequency and multi-threaded workloads previously limited by the power.
EXPO stands for Extended Profiles for Overclocking, and it's AMD's way to enable easy memory overclocking for their DDR5 platforms.
EXPO allows memory vendors such as G.SKILL to program higher performance settings onto the memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting, so it saves you from lots of manual configuration. Upon entering the BIOS, the boost frequency at one active thread is about 5416 MHz, and the average boost frequency gradually trails off to 5099 MHz when all cores are active. In light single-threaded workloads, all cores in CCD0 can boost to 5424 MHz, and all the cores in CCD1, 2, and 3 boost to 5050 MHz. We reran the benchmarks and checked the performance increase compared to the default operation. While the Ryzen Threadripper Pro 9975WX is definitely limited by power, as we saw in the stress test results of the previous OC strategy, unleashing the power doesn't have an enormous impact on performance. However, the performance uplift is pretty uniform across the board. The geomean performance improvement is plus 4.93%, and we get a maximum improvement of plus 14.93% in PY prime. Across the various OCCT workloads, SSE, AVX, AVX2, and AVX512, enabling PBO increases the operating frequency by up to 13.42% or 551 MHz. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 4855 MHz, and CCD1 to 3 average effective clock is 4522 MHz with 1.13 volts. The average CPU temperature is 93.7 degrees Celsius. The average CPU package power is 588.5 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 5045 MHz, and CCD1 to 3 average effective clock is 4671 MHz with 1.172 volts. The average CPU temperature is 84.6 degrees Celsius. The average CPU package power is 541.2 watts.
In our second overclocking strategy, we tune the parameters governing the Precision Boost algorithm with the tools provided in the Precision Boost Overdrive 2 toolkit. Fused maximum frequency, or Fmax, is one of those Precision Boost limiters governing the CPU performance. Specifically, the Fmax limit defines the maximum allowed frequency for all the cores in your CPU. For CPUs that have multiple CCDs, just like this Ryzen Threadripper Pro 9975WX, each CCD has its own Fmax as well. For example, for CCD0, it's 5450 MHz, but CCD 1, 2, and 3 are limited to 5050 MHz.
Boost Clock Override, or Fmax Override, is one of the tools available in the PBO 2 Overclockers toolkit. It allows the user to override the arbitrary clock frequency limit between minus 1000 MHz and plus 200 MHz in steps of 25 MHz. With a plus 200 Fmax boost override, the new maximum boost frequency for CCD0 is 5650 MHz, and for the other CCDs it's 5250 MHz.
It's important to note that the Fmax boost override doesn't act as an offset. Instead, it adjusts the upper ceiling of the allowed frequency. Scaler is a tool that allows you to override the warranted silicon stress level, or FIT, in order to achieve higher frequencies and higher performance.
You can adjust the maximum allowed FIT level to 10 times higher than the factory fused limit. While the tool offers precise granularity, typically, you'll find the available options to range between 1x and 10x in steps of 1 multiple.
The effect of increasing scaler is that the CPU will pursue more aggressively higher voltages, which in turn results into higher frequencies and higher performance. The usefulness of the scaler tool depends on architecture to architecture, but it seems that with the Ryzen Threadripper 9000 series, it's actually quite a useful tool.
When all cores are active, the maximum voltage is 1.31 volts. The maximum voltage when a single core is active is 1.45 volts. we find that in an all-core workload, the maximum allowed operating voltage significantly increased from 1.31 volt to 1.365 volt after setting 10x scalar.
Curve Optimizer is perhaps the most important tool in the Precision Boost Overdrive overclockers toolbox. It's most commonly known as an undervolting tool, but for Ryzen CPUs, it kinda also works as an overclocking tool. To explain why that is, let's start with the basics, the voltage frequency curve.
Here's the default voltage frequency curve of my Ryzen Threadripper Pro 9975WX processor. You'll notice that there are in fact 4 curves. That's because the Ryzen Threadripper Pro 9975WX has 4 CCDs with quite different characteristics. We can immediately make a simple but redundant observation. The higher the frequency, the higher the voltage. For example, CCD 0 requires only 1.1 volt for 5 GHz. However, we need 1.25 volt for 5350 MHz. This also applies to the other CCDs. For example, on CCD 1, 1.1 volt gets us 4450 MHz, whereas we need 1.3 volt for 5025 MHz. Compared to the other Zen 5 VF curves I've been tracking over the course of the various SkatterBencher guides, we find that CCD 0 is an exceptional CCD. We can do 5 GHz at 1.1 volt. However, CCDs 1 to 3 are pretty bad. At 1.3 volt, they trail about 350 MHz behind the worst Zen 5 curve we tracked to date, and that's the one of the Ryzen 5 9600X. Although it's not obvious from the VF curve, the maximum allowed voltage is 1.31 volt when all cores are active. The Precision Boost 2 algorithm utilizes the VF curve to find what's the maximum possible frequency at 1.31 volt. As I showed just a minute ago, we can use the Fmax boost override and scalar tools to increase the frequency ceiling by another 200 MHz and allow for higher frequency boosting. That further extends the default VF curves to 5650 MHz for CCD 0 and 5250 MHz for CCD 1, 2, and 3. Note that all the other Precision Boost rules still apply. So even though we have a higher frequency ceiling, because some frequency points are above the voltage threshold, we won't see those frequency boosts in all core workloads, however light they may be. If we set a negative curve optimizer, we can shift the entire voltage frequency curve along the voltage axis, and suddenly we need less voltage for every operating frequency. For example, at default, for 5 GHz, CCD 0 needed about 1.1 volt. However, with a -30 curve optimizer, now we only need 1.01 volt. And the same observation applies to CCDs 1, 2, and 3. Moreover, the frequency is also boosting higher. The highest frequency with all 32 cores active has increased to 5625 MHz on CCD 0 and to 5250 MHz on the other CCDs. These higher frequencies are now possible because our curve optimizer undervolting pulled them below the voltage threshold.
Curve Optimizer is a very powerful tool. It's simple, but not simplistic. And the more you dig into the details on how it works, the more intricate it becomes to figure out how to best use it in your situation. The traditional way of using Curve Optimizer is to use it for setting a negative voltage offset, and it helps in 2 ways.
First, undervolting lowers the operating voltage, temperature, and power consumption. Second, as a consequence, the Precision Boost 2 algorithm can leverage the additional headroom to boost to higher frequencies.
So you tend to get lower temperatures and higher performance. It's a win-win. However, there are a couple of caveats to using Curve Optimizer.
Curve Optimizer impacts the entire voltage frequency curve, so it affects stability across the entire range of operating frequencies, from 600 to 6000 MHz. The same Curve Optimizer value impacts differently across the curve. If you're lucky, your CPU's undervolt margin matches how Curve Optimizer offsets the voltage across the curve. Then you'll maximize the performance gains. But if you're unlucky and one part of your CPU's VF curve has a lot less margin, then your curve optimizer tuning journey will be a rough ride.
Of course, having a CPU with multiple CCDs, each having their own VF curve, makes it more difficult or more challenging to tune than a chip with just a single CCD.
Curve Optimizer is available on a per CPU, per CCD, and per core basis.
The manual tuning process for Ryzen Threadripper CPUs can become quite convoluted because we need to tune for a large variety of workloads, going from single-threaded light workloads to all-core heavy AVX workloads.
I want to emphasize this point and refer to my Ryzen 9 9950X overclocking guide, where I demonstrated that the VF curve changes depending on the workload. With a dynamic voltage frequency scaling technology like Precision Boost 2, it's vital to test a wide variety of scenarios as opposed to just a heavy all-core workload pushing the power consumption to its limit. Sometimes your all-core AVX workload can be entirely stable, but you get blue screens in games. I identified 4 typical workloads that tend to show early signs of instability. So when I increase the negative curve optimizer setting in steps of 5 points, I quickly check stability with each of these applications. Once I find an instability, I back off on the curve optimizer and check stability across the benchmark suite. Personally, I found that the OCCT AVX512 all-core workload was the first to show signs of instability with this particular CPU.
An error has been detected.
For multi-CCD Ryzen Threadripper CPUs, I recommend you use per CCD curve optimization because they're pretty different in quality and they have a different Fmax as well.
Upon entering the BIOS, the boost frequency at one active thread is about 5,597 MHz, and the average boost frequency gradually trails off to 5,330 MHz when all cores are active. In light single-threaded workloads, all cores in CCD0 can boost to over 5.6 GHz, and all cores in CCD1, 2, and 3 boost to 5,250 MHz. We reran the benchmarks and checked the performance increase compared to the default operation. Fmax, Boost Override, Scaler, and Curve Optimizer work together to provide us with higher and longer frequency boosts in all kinds of workloads. We find that the performance improves uniformly across the board in pretty much every workload. Geomean performance improves almost 6 percentage points. We get a maximum improvement of plus 17.32% in Y-Cruncher. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 5,093 MHz, and CCD1, 2, 3 average effective clock is 4,926 MHz with 1.106 volts. The average CPU temperature is 92.3 degrees Celsius. The average CPU package power is 589.6 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 5,293 MHz, and CCD123 average effective clock is 5,085 MHz with 1.205 volts. The average CPU temperature is 95 degrees Celsius. The average CPU package power is 612.7 watts.
In the third overclocking strategy, we delve into optimizing the memory subsystem. Now, on AMD Shimada Peak Threadripper processors, the memory subsystem consists of 3 major parts: the Infinity Fabric, the memory controllers, and the system memory. Now, seasoned Ryzen overclockers know that these parts used to be tightly coupled together, but on modern Ryzen CPUs, we can tune them independently. Or so I thought.
The fabric frequency, or F-clock, is generated by the SoC PLL derived from a 100 MHz reference clock input. The reference clock is multiplied by the F-clock ratio, which you can configure in the BIOS. The standard operating frequency of the Infinity Fabric is 1800 MHz, but on many boards you'll find it runs over 2 GHz when Precision Boost Overdrive is enabled. That said, it doesn't seem there's much overclocking headroom beyond 2 GHz. I managed to set 2100 MHz for this overclocking strategy, however anything higher couldn't boot reliably, not even with voltage adjustments. Speaking of the voltage, the Infinity Fabric voltage is provided by the VDD-G voltage supply, derived via an integrated voltage regulator from the VDD-IO voltage rail. There's a total of 8 VDD-G voltage rails available for manual adjustment. AMD Shimada Peak has 4 or 8 DDR5 unified memory controllers, depending on whether you're using a Pro or a non-Pro chip. Each memory controller provides 2 32-bit memory channels. The Unified Memory Controller Frequency, or U-clock, is derived from the UMC clock, one of the SoC PLLs. The memory controller frequency is tied directly to the system memory frequency. Unlike other Ryzen platforms, it can only run at half the memory frequency. That means we cannot force the memory controller to run at the same frequency as the system memory by setting uclock div1 mode to uclock equals memclock. The VDD-CR SoC voltage rail provides the external power for multiple internal voltage regulators on the SoC for the various IP blocks, including the memory controller. The VDD-11 voltage rail is related as it provides the external power for the VDD-P DDR5 bus signaling.
The last piece of optimizing the memory subsystem is tuning the memory timings. And for that, I rely in part on the ASUS memory presets. ASUS memory presets is an ASUS overclocking technology that provides us with a selection of memory tuning presets for certain memory ICs.
The presets will adjust the memory timings and voltages. The Asus Pro WS WRX90E Sage SE motherboard with BIOS 9901 sports 11 memory profiles for Hynix memory ICs. Since we're interested in simply adjusting the memory timings, we can try the Hynix 8400 1.45 volt 2x24GB single rank preset.
While I'm absolutely grateful that I have access to these parts prior to launch, it also means that the platform isn't fully tuned yet. And so I found that both the EXPO as well as the memory preset were tuned a little bit too tightly, and they wouldn't be stable for like a multi-hour stress test.
Furthermore, it was quite easy to get a bit higher performance by manually adjusting the following memory timings to 1. After tuning, our AIDA64 performance improved quite significantly. We got about plus 20% extra bandwidth and better latency by enabling EXPO, and the memory tuning then added another 7 to 15% on top of that. Upon entering the BIOS, we reran the benchmarks and checked the performance increase compared to the default operation. As we've seen with other modern platforms, Tuning the memory timings can have a not insignificant impact on system performance, especially in workloads which are memory dependent. We see this behavior in specific multi-threaded workloads like PY Prime, Y-Cruncher, AI Benchmark, and Geekbench. The geomean performance improves another 3 percentage points, and we get a maximum improvement of plus 51.81% in PY Prime.
In the final overclocking strategy, I'm pursuing a manual overclock for this 32-core CPU. Now, there's an argument to be made that manually overclocking an AMD Ryzen CPU, especially the ones with multiple CCDs, doesn't make a lot of sense. And the argument for that is that when you switch to manual overclocking, you lose any of the Precision Boost features. For example, this CPU can boost to 5450 MHz in light single-threaded workloads, but when we switch to manual overclocking, it would only run that fixed frequency. Now, there is also a possible upside. The automatic frequency boosting technologies typically leave a little bit of headroom on the table, both in terms of voltage and frequency. So for certain applications, it's possible that manual overclocking will give you higher frequency than the automatic boost.
Let's have a look at the Ryzen Threadripper 9000 CPU clocking and voltage topology. The standard Shimada Peak platform has a 48 MHz crystal input to the integrated CG-PLL clock generator. The CG-PLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. As a whole, this provides CPU clock frequency granularity of 25 MHz. Each CCX has its own PLL, with the cores within that CCX running at the same frequency. The Shimada Peak platform supports eClock, however, only in synchronous mode, not in asynchronous mode. So that means that if we increase the eClock, it will affect all the clocks in our CPU. The voltage of the CPU cores is provided by not one but two VDDCR CPU voltage rails. It can be challenging to figure out which cores are powered by what voltage rail. Counterintuitively, CCDs 0 and 3 are powered by VDDCR CPU 0, and the other two are powered by VDDCR CPU 1. The voltage can be configured in two ways. Either you set the target VID by programming the CPU registers, or directly set the target voltage of the voltage regulator.
Choosing the appropriate voltage is a trade-off between increased overclocking headroom, the thermal challenges that come with increased voltage, and of course, consideration of the CPU lifespan. It's with that last thought that we kick off the most tedious or most exciting part about Ryzen Threadripper manual overclocking: tuning the CCXs.
Our limiting factor will ultimately be the cooling solution, as power consumption increases exponentially with the operating voltage and temperature scales somewhat linearly with power consumption. The maximum voltage will be determined by the application we're tuning for. In this case, I picked a 30-minute OCCT AVX512 CPU stability test, since I need the CPU stable enough to run a number of AVX512 workloads. The next step is to set a fixed CPU ratio and check the maximum temperature when running our workload. If there's thermal headroom left, increase the operating voltage. In my case, I pick a CCX ratio of 45x for all 4 CCDs and a VID of 1.1 volt. We find this gives a temperature of 70 degrees Celsius and an effective voltage of 1.035 volt. That means we can further increase the voltage until we get to about 90 degrees Celsius.
Once we know what's the maximum voltage, we can switch to tuning each CCX individually. You can just increase the ratio of one CCX until you see signs of instability and then back off, and then try the next CCX and the next one and the next one until you found the maximum frequency for each of the CCXs.
In this table, you can find the maximum ratio for each CCX. We ended up with an average frequency of 4,825 MHz with 1.16 volt VID, which under high load drops to about 1.08 volt. As a reminder, the values in this table are for my specific system and specific stability test. Your CPU may have wildly different values depending on the CPU sample, cooling and motherboard, and your chosen stability test. Upon entering the BIOS, the boost frequency at one active thread is about 5050 MHz, and the average boost frequency gradually trails off to 4826 MHz when all cores are active. In light single-threaded workloads, all cores in CCD0 can boost to 5050 MHz. We reran the benchmarks and checked the performance increase compared to the default operation. As expected, we see a pretty mixed impact on the performance, as some benchmarks improve significantly over stock, whereas others are actually slower than stock. That's the trade-off we discussed before when a manual overclock disables the sky-high single-core boost frequencies of Precision Boost technology. We got a maximum improvement of plus 47.26% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 5042 MHz and CCD123 average effective clock is 4742 MHz with 1.08 volts. The average CPU temperature is 89.8 degrees Celsius. The average CPU package power is 562.8 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 5042 MHz and CCD123 average effective clock is 4742 MHz with 1.092 volts. The average CPU temperature is 76.4 degrees Celsius. The average CPU package power is 478.6 watts.
Alright, let's wrap this up. This was my first go at overclocking the AMD Ryzen Threadripper 9000 workstation CPUs. And it's without a doubt the most powerful workstation CPUs I've ever had the pleasure of overclocking. The overclocking experience is pretty smooth, though there are a couple of oversights. First of all, not being able to run uclock equals memclock is a fail. That should not happen on a Ryzen Threadripper platform, period. Second, not having a synchronous eClock is unfortunate. I know the platform is a little bit more complicated than a desktop Ryzen version, but still, we've seen on the desktop side, starting from Ryzen 7000 and also on Ryzen 9000, that it's a very useful tool once we hit these Fmax limits. And given the undervolting capability of this CPU, I'm sure we would have been able to get 5.7, maybe 5.8 in single-threaded workloads, and maybe 5.4 GHz in an all-core workload. That would have been a beast of a CPU. Lastly, I think we need to overhaul the Fmax Boost Override tool for multi-CCD Ryzen CPUs. Currently, CCDs 1, 2, and 3 are always trailing 400 MHz behind CCD 0. And while they're definitely different quality, I don't think the gap in frequency should be that large. I think we should be able to set the Fmax for each CCD individually, and I think we should also be able to set it higher than plus 200. Setting it per CCD makes a lot of sense because we already have Curve Optimizer on a per CCD basis. Anyway, that's it for this video. I want to thank you for watching, the patrons for the support, and the YouTube members for the support. If you have any questions, drop them in the comment section below. If you want to read through my BIOS settings, check out the written version up on my blog. And that's it. See you next one.